Okay, so welcome back to another video. Here's a nice little closed form that we want to solve with the following infinite sum. We have the infinite sum from n is equal to 1 to infinity of 4 to the power negative n times sine of 4 to of 2 to the power negative n theta. So this one's actually not going to be too long of a procedure because the first step we're going to be using is a nice little identity that I don't think a lot of you guys know about. I didn't even know about it myself until I actually did the research behind this. I'm going to prove that identity as well. So after using that identity, it actually just follows from some nice simplification, and this has to continue. Eventually, we have to continue using the limit, and that actually involves a little bit of calculus involved. L'Hopital's rule will be involved throughout that procedure, and it actually just comes down to something simple as that. Not really needs to be, there's not really a whole lot going on. It looks like there should be a lot going on based on how we have sine of 4 to some input and then 4 to the power negative n of an infinite sum, but it's not really something you need to worry too much once I show you everything. So with that, why don't we actually just jump right in. Here's our nice little identity we'll be using. We're going to be using that sine of 4 to the x is equal to sine square of x, and then subtract 1 divided by 4 times sine square of 2x. Bet you guys have never seen an identity like this before, so why don't we actually verify this? So let's prove this. So we know that sine to the power 4 of x, it has that nice identity that from this closed form, you've definitely seen this many times whenever you're doing trigonometry. It comes to 3 divided by 8 minus 1/2 cosine of 2x, and then add this with 1 divided by 8 times cosine of 4x. Well, let's actually do a little bit of substitution and change things up for both our cosine 2 of x and cosine 4 of x. As you see, this will yield 3 over 8 and then minus 1/2. We know that cosine of 2x has the nice identity of 1 subtract 2 times sine square of x. And then same thing, 1 over 8. Cosine of 4x has that nice identity of 1 subtract 2 times sine square of 2x. Okay, so now we just simplify some things forward. So let's see, 3 over 8, and then just distribute the 1/2 into everything here. So minus 1/2, and then plus sine square of x. Add this with 1 divided by 8, and then subtract 1 divided by 4, then times sine square of 2x. Okay, and then we can clean things up a little further so that we are just left with sine square of x. And you can see we have 3 over 8, and then minus 1/2 plus 1 over 8. So that's just going to get rid of itself, and then we're just left with 1 divided by 4 times sine square of 2x. Okay, that completes that little identity proof. So we can actually use that to substitute our given infinite sum to help reducing things a little bit easier. So now our infinite sum, well, let me just write in the series. So 4 to the power negative n, if you just replace with all the pieces together and into the identity over here, so 4 to the power negative n, so sine to the power 4 of 2 to the power negative n, then theta. Then using the identity, so we have 4 to the power n, then times sine to the power, or sine square of 2 to the negative n theta, and then subtract 4 to the n minus 1 sine square of 2 to the minus, so I'm going to write this in parentheses, n minus 1, and then theta. Okay, so now with this, you're actually going to notice something that's very interesting. So now if I just actually write this whole sum out, so our infinite sum, n is equal to 1, and then if I actually just substitute this whole thing over here, so give me a second to write this out in full. Okay, so if you actually evaluate each term one at a time, and if you actually notice the sequence as you actually add all these terms together, this is actually going to be a telescoping series. So what that means is that the only terms you're left with is the first and the last term. And so then we can actually just write this in terms of a limit. So let me actually go to the top over here, and we can continue forward with our writing. So then this entire thing will just be the limit as n approaches infinity. So that's actually just the last term that we're going to evaluate. So the limit as n approaches infinity of 4 to the power n, and then sine square of 2 to the negative n then times theta, and then subtract with our first term evaluated, which is just going to be sine square of theta. So now this just leaves us with this to calculate the limit. So if you'll notice that this is actually in terms of infinity, but because this is just one single function, we can actually write this in terms of a rational function such that if you were to take that limit, then we get something of an indeterminate form. So let me rewrite this. So that means I have the limit as n approaches infinity. We can write this as the following. So we can write this as sine of 2 to the negative n theta, then divided by 2 to the negative n, then that quantity square, and then subtract sine square of theta. Okay, so that means you take this, then you're going to see that, of course, this whole thing is going to be in a form of a 0 over 0 indeterminate form. So that means we will have to apply L'Hopital's rule, meaning that we have to take the derivative of our numerator and the derivative of our denominator. So why don't we actually do that? So that means taking the derivative, we would have, let's see, so the limit as n approaches infinity, and then we have to take this in respect to n. So d divided by dn of sine of 2 minus n theta, and then divided by the derivative of, in respect to n, of 2 to the negative n. Then taking that derivative of our numerator, we're going to have negative 2 to the power of negative n, then times ln of 2 times theta, and then times the derivative of sine, so that means cosine of 2 minus n, then theta. All this being divided by, so derivative of this again is negative 2 to the power of negative n, then ln of 2. So that means we have to take the limit as it approaches infinity. I forgot to write the limit again, but that's totally fine. So you're going to notice that this is actually just going to cancel out. So I can actually write in this line, the limit as n approaches infinity of theta, and then cosine of 2 to the negative n, then theta. Then of course, theta is just a constant, just can go outside. But if you take that, that means 2 to the negative infinity, that's just going to be 0. So therefore, this is just going to be simply just theta. And then going back into over here, so that means I have theta square, then minus sine square of theta. And I didn't need to write the parentheses, there was no point, because we can just simply just write theta squared minus sine square of theta. And then that is our nice little closed form to finish off this problem right over here. So all follows from just one big trig identity with signs that, again, I'm sure, I don't think a lot of you guys may not know about this. I certainly have it. So we just break this down just to verify the proofs due to simplifying. Then there comes the limit, then apply L'Hopital's rule to, get this nice little simple answer over here. So yeah, that's pretty cool if you ask me.